Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to finish up chapter 4 for our MCAT Organic Chemistry playlist, and we left off at objective 3, which is titled Oxidation Reduction Reactions. Oxidation reduction reactions are also known as redox reactions, and they involve the transfer of electrons between chemical species that leads to changes in their oxidation states. Oxidation is defined as the loss of electrons, while reduction is the gain of electrons. A useful way to remember this is with the mnemonic Leo the lion says grr. Leo stands for losing electrons is oxidation, and grr stands for gaining electrons is reduction. Because oxidation involves the loss of electrons, the species undergoing oxidation becomes more positively charged. On the other hand, reduction involves gaining electrons, so that results in a more negatively charged species. In every redox reaction, there is always an electron donor and an electron acceptor. The reducing agent is going to be the species that donates electrons, meaning it undergoes oxidation, while the oxidizing agent is the species that accepts electrons and is therefore reduced in the process. One example of a redox reaction is the reaction between magnesium and hydrochloric acid. In this reaction, magnesium is oxidized because it loses electrons to form this magnesium 2 plus cation. And then the hydrogen ions in hydrochloric acid, they're going to be reduced because they gain electrons to form hydrogen gas. Since magnesium donates electrons, it's known as the reducing agent, while the hydrogen ions, which accept these electrons, they function as the oxidizing agent. One way to understand redox reactions is by considering how oxidation and reduction affect the oxidation state of an atom. Oxidation increases an atom's oxidation state, while reduction decreases it. On the other hand, for organic chemistry, oxidation can be recognized as an increase in the number of bonds to oxygen or other electronegative atoms, often accompanied by the loss of hydrogen atoms, while reduction typically involves a decrease in bonds to electronegative atoms and an increase in hydrogen content. With that being said, let's go through some common oxidation reactions that are important to know for the MCAT. Starting with alcohols, the oxidation pathway depends on whether the alcohol is primary, secondary, or tertiary. Primary alcohols can be oxidized to aldehydes using PCC, which is pyridinium chlorochromate, or chromium trioxide in pyridine, which selectively stops at the aldehyde stage because PCC is a mild oxidizing agent. However, under stronger oxidation conditions, primary alcohols can be oxidized all the way to carboxylic acids using chromic acid, potassium permanganate, or hydrogen peroxide. These strong oxidizing agents allow the oxidation to proceed fully, and it ensures that the carbonyl carbon reaches its highest oxidation state. As for secondary alcohols, they undergo oxidation to form ketones using PCC or chromium trioxide in pyridine. Unlike aldehydes, ketones do not have a hydrogen atom attached to the carbonyl carbon, so it prevents further oxidation under normal conditions. Aldehydes, they can be further oxidized to carboxylic acids using chromic acid, or potassium permanganate. This oxidation is actually highly relevant in biological systems, particularly in metabolic pathways where these aldehydes serve as intermediates before they're converted into carboxylic acids for further processing. For aromatic compounds like benzylic alkyl groups, like those found in toluene derivatives, these can be oxidized to benzoic acid using potassium permanganate. So this reaction occurs regardless of the length of this alkyl chain. Next, let's talk about alkenes. When oxidizing alkenes, the choice of reagents determines whether the products are aldehydes and ketones or fully oxidized carboxylic acids. Let's start with ozonolysis. This is a key reaction where ozone cleaves the carbon-carbon double bond. The outcome depends on the subsequent workup setup. When the reaction is followed by a reducing agent such as zinc or dimethyl sulfide, the alkene is split into aldehydes and ketones. This is known as a mild ozonolysis reaction, meaning the oxidative conditions are not strong enough to further oxidize aldehydes into carboxylic acids. On the other hand, when ozonolysis is performed with an oxidizing workup, such as hydrogen peroxide, or under strong oxidative conditions with potassium permanganate, heat and acidic conditions, any aldehyde that forms will further be oxidized to carboxylic acid. And this is because aldehydes are susceptible to oxidation, whereas ketones remain unaffected under these conditions. Alkenes can also undergo hydroxylation to form vicinal diols, which are compounds that contain these two hydroxyl groups on adjacent carbon atoms. This transformation is achieved using osmium tetraoxide or potassium permanganate in basic conditions, and here the hydroxyl groups are added across the double bond in a syn addition. These diols can then be further oxidized into aldehydes or ketones using lead tetraacetate or any of the other reagents shown here, which will cleave the carbon-carbon bond between the hydroxyl-bearing carbons. Another key oxidation reaction for alkenes is epoxidation, in which some acids such as metachloroperoxybenzoic acid, MCPBA, converts the alkene into an epoxide. Epoxides are highly reactive due to the ring strain in this three-membered cyclic ether, and that makes them valuable intermediates in organic chemistry. What about alkynes? Alkynes, they can be cleaved into carboxylic acids under ozone, followed by water, or potassium permanganate under heat in an acidic medium. This reaction efficiently breaks down triple bonds and it leads to fully oxidized carboxyl groups. Finally, oxidation can also modify ketones under specific conditions. Ketones can be oxidized into esters using MCPBA. This reaction inserts an oxygen atom adjacent to the carbonyl carbon, expanding the functional group from a ketone to an ester. Now, let's do the same thing for common reduction reactions that are important to know for the MCAT. Aldehydes and ketones are readily reduced to primary and secondary alcohols, respectively. This reaction can be carried out using lithium aluminum hydride or the milder reducing agent, sodium borohydride. Because sodium borohydride is less reactive, it is generally only effective in reducing aldehydes and ketones, while lithium aluminum hydride is strong enough to reduce a broader range of functional groups. Carboxylic acid requires a much stronger reducing agent because they are more oxidized than aldehydes or ketones. Lithium aluminum hydride in ether is commonly used for this purpose, followed by protonation with water, ultimately yielding a primary alcohol. Esters undergo a similar reduction, but they produce two products, a primary alcohol and an additional alcohol fragment that corresponds to the ester's OR group. Amides, which contain a carbonyl adjacent to a nitrogen, can be reduced to primary amines when they're treated with lithium aluminum hydride in ether, followed by an aqueous workup. Unlike carboxylic acids and esters, which are reduced to alcohols, the reduction of amides removes the oxygen entirely and forms an amine rather than an alcohol. For the reactions that we covered in this objective, I want to note that we're going to revisit them in the coming chapters. So you're going to see this content more than once and will definitely make it easier for you to learn. So keep that in mind. If you don't get it yet, that is totally okay. We're going to go over these reactions in details over a couple of chapters. But with that, we've completed Objective 3, and we can now move into Objective 4. A key aspect of understanding organic reactions is recognizing which sites in a molecule are most reactive and how different functional groups behave in the presence of one another. This concept is known as chemoselectivity, which refers to the preferential reaction of one functional group over others when multiple reactive sites are present in a molecule. Recognizing chemoselectivity is essential for predicting reaction outcomes and also for understanding selectivity in chemistry. The reactive site of a molecule depends on the type of chemistry that is occurring. On the MCAT, two key reactive sites to consider are the carbonyl carbon, which is highly reactive due to that partial positive charge on carbon from the electronegative oxygen. This makes the carbonyl carbons electrophilic and susceptible to attack by nucleophiles. The second site to consider is the substrate carbon in substitution reactions, which is another very important reactive site. In these cases, nucleophilic substitution can occur when a nucleophile displaces a leaving group, as we saw with SN1 and SN2 mechanisms. In many organic chemistry reactions, nucleophilic and redox reactions tend to act at the highest priority functional groups. The most oxidized functional group is often the most reactive site, meaning that oxidation, reduction, or nucleophilic attack will typically target the functional group with the most bonds to oxygen or other electronegative atoms. However, chemists can manipulate reactivity by taking advantage of steric hindrance. Steric hindrance refers to the physical crowding of bulky groups around a functional site, which can either slow down or prevent a reaction from occurring. This property can be used to selectively target certain functional groups while avoiding reactivity at others. Additionally, steric hindrance is useful for protecting functional groups that might otherwise react in an undesirable way during a reaction sequence. Protection groups can be introduced to temporarily mask a functional group and then later be removed under specific conditions to restore its reactivity. Now, don't worry if this seems overwhelming. Again, this is just a preview of what we're going to see in later chapters with more details. This is just an introduction to some fundamental ideas and rules. Now, building on our discussion of chemoselectivity, we can now turn to how we can systematically approach reaction problems. A strong understanding of reactivity and selectivity allows us to predict how different functional groups will behave in a given reaction. To do this effectively, we need a structured approach to analyzing reaction mechanisms. When solving reaction problems, the first step is always to identify all of the functional groups in the given molecule. Each functional group has characteristic reactivity, and recognizing them is essential for determining the type of reaction that might occur. Next, we analyze the reagents to understand their function. Are they oxidizing agents, reducing agents, nucleophiles, or electrophiles? By knowing what each reagent does, we can anticipate how it will interact with the molecule. From there, we identify the most reactive functional group in the given conditions. As we discussed earlier, the most oxidized functional group often serves as the most reactive site, particularly in redox reactions and nucleophilic reactions. Once we establish this site of reactivity, we then determine the first step of the reaction. Many organic reactions, they occur in sequential steps. So understanding that initial transformation is key to predicting the overall outcome. Finally, if applicable, we can consider stereospecificity or stereoselectivity. Does the reaction favor one stereoisomer or over another? Does it lead to the retention of configuration or not? These considerations become especially important in substitution reactions and again in redox pathways. So now let's apply these principles to a multi-step reaction problem. For this problem, we're given the following starting molecule. This molecule undergoes 3 transformations, and we need to figure out what the molecule looks like after each step. The molecule provided contains an alkane backbone, a ketone, and an ester functional group. Both the ketone and ester contain carbonyl carbons that are electrophilic, making them possible targets for nucleophilic attack. Additionally, we need to consider the possibility of reduction, as both of the carbonyl oxygens are potential sites for transformation. Now, the first reagent that's introduced is ethylene glycol in the presence of toluene sulfonic acid and benzene. Ethylene glycol is a diol, and it is commonly used as a protecting group for aldehydes and ketones, and it forms a cyclic acetyl group. This protection prevents the ketone from undergoing unintended reactions in subsequent steps. So from this first step, we do nothing to our ester group, but our ketone is now protected through this protection group, and it forms a cyclic acetyl. The second step involves lithium aluminum hydride and THF. Lithium aluminum hydride is a strong reducing agent, which selectively reduces the ester functional group, and it does it by transforming it into a primary alcohol while leaving that protected ketone intact. So, this is amazing. We're getting to see how the protected ketone is not affected by a reducing agent. Finally, the third step involves an acidic workup using hydronium ion and heat. These acidic conditions hydrolyze the acetyl protecting group, and it regenerates the original ketone functional group. So now we have our ketone group back, but our ester functional group was transformed into a primary alcohol. And with that, we've completed this problem. At the end of the sequence, once again, we're left with a primary alcohol from the reduced ester, And we have a restored ketone from the deprotected cyclic acetyl. We have completed this chapter. I hope that it has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.